War is a great way to develop technology. As sad as it is, because war is brutal. The primary reason for that is everyone wants to have the best weapons because it gives them the advantage on the battlefield.
More than any other conflict before or since, World War II was a battle for supremacy at sea.
They invented tanks that could swim. There were submarines that were purpose-built to carry aircraft and launch them. There were even ships made of concrete. So there were a wide variety of really unorthodox and unusual weapons that were created.
Many of the deadliest campaigns either started or ended in the ocean. Victories or defeats offshore, triggering major turning points on land.
And as the time progressed and the war dragged on, more and more weapons development went on. You had all kinds of new technologies, new weapons. They were all gradually more and more sophisticated.
With vast stretches of water to cover, speed and strength were the key to success, but so too was stealth. In the early hours of December 7th, 1941, Japan unleashed a devastating attack on Pearl Harbor. Hundreds of bombers launched from 6 aircraft carriers, their aim to cripple America's Pacific Fleet in a surprise aerial assault. The success of the Hawaiian bombardment emboldened Japan. Its naval command began formulating a plan to strike at the US mainland. But with America now on alert, this time they would approach from under the water. And for that, they'd need to think big.
The E-400 was the idea of Admiral Isoroku Yamamoto, who was the commander-in-chief of the Imperial Japanese Navy at the start of World War II. And what's interesting is that Yamamoto conceived of a fleet of 18 gigantic subs, far bigger than any sub that had ever been built before. In fact, far bigger than any sub until the late 1950s when the US started fielding nuclear submarines.
The E-400s were designed to be just over 120 meters long and displaced 5,500 tons. At the time, the largest submarine the US Navy fielded, the USS Argonaut, displaced 2,710 tons, more than half the weight of the E-400s. But that extra weight wouldn't slow them down. 4 diesel engines would provide 7,700 horsepower of propulsion, allowing them to achieve a speed of almost 19 knots, making them one of the fastest subs in the war. But what would truly set them apart was their range.
The subs could travel 1.5 times around the world without refueling. Now, no sub during World War II was capable of any kind of range like that except for the E-400 class. And that was one reason why Yamamoto wanted them to be built so big, so they would have enough fuel that they could travel that distance.
Yamamoto believed these subs would be a game changer, capable of winning the war for Japan. But staying power alone wouldn't be enough to strike at the heart of America.
Each sub would carry 3 attack bombers in a watertight deck hangar that they could launch off their bow when surfaced by pneumatic catapult. And the idea is these subs would travel from Japan to the east coast of the United States, surface off New York City and Washington, D.C., and launch a second surprise aerial attack as a follow-up punch to Pearl Harbor.
To have any chance of success, the E-400s would need to swiftly transform into mobile launching pads as soon as they were in range of their target. Once the subs surfaced, all 3 Aichi M6A Serans could be armed with 2 250-kilogram bombs, and ready for action within 45 minutes. After completing their mission, the float planes would be retrieved by a collapsible crane before the E-400 would once again disappear beneath the waves.
You know, a lot of people think that this was a crazy idea. I don't think they really understood Yamamoto's logic. Yamamoto had lived and studied in the US. He spoke English, he attended Harvard University. He subscribed to Life magazine. He had a really good understanding about what America was all about, and particularly about our production capacity. And he realized that even though Pearl Harbor was a success, it only knocked the US out of the war for 6 months. So he wanted to come up with something that would be psychologically devastating.
This degree of ingenuity would take time to build. Production began in 1942.
There were a lot of obstacles to the construction and deployment of the E-400 subs. You know, Yamamoto wanted them built quickly, but these subs were so huge and required so much material, particularly steel, which was in short supply as the war continued on, is that it took almost the whole war to complete just 6 of these subs. And on top of that, Yamamoto, who was obviously the chief defender of this program, he was killed in 1943 over Bougainville by U.S. Army Air Corps P-38 Lightnings. They shot his plane out of the sky. And once Yamamoto was dead, the greatest defender of that program died along with him.
Despite these setbacks, the first E-400s began floating off the production line in late 1944, early 1945. By the time the first models were ready for service, it was a case of too little, too late. Japan surrendered 2 days before they were due to attack the US naval anchorage in the Caroline Islands. They returned home to be handed over to the Americans, but the E-400s achieved at least one of their aims: the element of surprise.
Even though the US had broken the Japan Naval Code and knew where most of Japan's submarines were at any one time, the United States had no idea that Japan had this capability. It was a complete shock. The E-400 program was a top secret program, and the US never knew about either the subs or their ultimate mission.
While the E-400s never got the chance to prove their capabilities, their innovative design at least demonstrated that subs had the potential to play a frontline role in modern warfare.
What's so important historically about the E-400 subs is that they totally changed what a submarine was meant to do. Subs went from being scouts and sinking enemy ships to becoming the main leg of our nuclear defense arsenal. And that can be traced back to the original conception of the E-400 subs.
As Japan and America battled for control of the Pacific, the Allies were struggling against a formidable foe in the Atlantic. For more than 3 years, German U-boats had played havoc in the vital shipping channel between the United States and Great Britain, sinking thousands of cargo vessels. But as the desperate Allies developed their sonar capabilities, they could now start pinpointing these hidden menaces and begin turning the tide against Germany's naval campaign. To regain control of the Atlantic, Hitler recognized the need for a faster, quieter, long-range vessel, the likes of which had never been seen before.
When the Type XXI was being developed, the Battle of the Atlantic was at a crucial tipping point. It was literally 50-50. The Germans knew that the existing submarines, however effective they were, and they were very, very effective, they only had a fairly limited capacity to stay underwater. And of course, the more they came on the surface, the more visible they became to enemy aircraft and enemy ships and so on. So the XX-1 was designed to create a submarine that could spend a great deal of time underwater, far more than the existing ones.
The plan was to create a vessel that could travel submerged for up to 3 days, almost triple the time of a Type 7, the hero of the Atlantic campaign. To do this, the Type 21 made use of an advanced diesel-electric engine that allowed the 21 to travel underwater at significantly higher speeds and for longer than any submarine that had come before. At 77 meters, it would be 10 meters longer than the 7, but its sail or conning tower would be streamlined to reduce drag. With these design elements incorporated, the Type 21 could maintain a top speed of 18 knots for 90 minutes while submerged. 3 times faster and for twice as long as the 7 could achieve under full power. While the Type 21, like previous U-boats, was submerged, it was powered by its large bank of batteries. To recharge these batteries required running the diesel engines, but these engines would quickly drain the U-boat's supply of oxygen when submerged. As such, earlier U-boats had to surface whenever they needed to recharge their batteries or risk suffocating themselves. This could be an incredibly risky maneuver as the U-boat was exposed while it recharged. An innovative snorkel system would allow the 21's diesel engine to access the oxygen without surfacing. In this way, the sub could recharge its batteries in as little as 4 hours every second day, while the Type 21 remained underwater.
It could have been a game changer, but they were not put into action until literally the last few months of the war. It's crazy. That was again a case where the Germans missed a golden opportunity.
Not only was the Type 21 designed to move with stealth, it was armed to cause maximum damage. The U-boat carried 23 torpedoes, which it could fire from 6 bow tubes. A hydraulic system allowed all 6 to be reloaded in under 10 minutes, less time than it took to load a single tube on the Type 7. It was to be the world's first truly modern underwater warship. The first operational Type 21 did not see service until March 1945, by which time it was far too late. The Battle of the Atlantic was over, and Allied troops were overrunning Germany.
Although 100 of them were built, only 4 of them were actually launched, and only 2 of them saw active service, and that purely as patrol boats. Although it's difficult to say, really, because they never fired a torpedo in anger, the probability is they would have been very effective. But by the time they did see service, it was far too late, because nobody in 1945 had any illusions that the Germans were going to win the war.
While the Germans never benefited from the Type 21s, the design was not entirely wasted. Post-war, these electric subs ended up in the hands of the Soviets, Americans, and British, and would eventually inspire some of the designs for Cold War submarines. Although the Type 21 didn't have the desired impact on the Battle of the Atlantic, it wasn't the only secret weapon that the Germans had developed to try to break the deadlock. And one unique development would attempt to combine a few secret weapons technologies. When Germany invaded France in May 1940, it unleashed a weapon destined to change the nature of modern warfare. The Naval rocket launcher could fire projectiles and highly explosive shells on Allied troops at ranges from 5.5 to almost 7 kilometers. They were developed in secret during the pre-war years, when the Treaty of Versailles prevented the Germans from building heavy artillery. These rocket launchers were considered such a success, the Nazis began working on ways to fire powerful missiles from as many platforms as possible, even testing the waters for a sub-based carrier. The concept of combining a rocket launcher with a U-boat was a logistical nightmare. There was not enough space to transport the weapons inside the existing fleet, so a plan was devised to mount the hardware on a sub's deck, and U-boat 511 was to be the test case. In May 1942, in a secret operation codenamed Project Ursel, the Type IXC sub was fitted with 6 solid fuel rockets and set sail for the Baltic Sea, where the new weapon system would be put to the test. The Wurfkorper projectiles were mounted at a 45-degree angle in front of U-511's conning tower. Once submerged, the U-boat would unleash a barrage of firepower from the 30-centimetre rockets, triggered by an electrical charge. While the test proved that it was possible to fire a rocket from 12 metres below the surface, with the weapons on board, the sub handled poorly, and the crew had very little control of the path of the projectile.
The original idea was to use them against shipping, but they quickly realised that wasn't going to work. They tried testing it, and they found this again and again, that the guidance system wasn't good enough, and it would probably have missed the target, and especially with a moving target like a ship, which obviously can try and take evasive action. So they thought it wasn't really worth the effort.
The Nazis shelved plans for a fleet of U-boat rocket launchers, instead devoting all resources to developing the world's first cruise missile. Hitler wanted a weapon capable of crossing the English Channel, and the V2 was the answer. Between September 1944 and March 1945, almost 3,000 of these guided missiles were fired at France, Belgium and England from bases in Northern Europe. Although less than half reached their destination, Hitler was still impressed and charged his scientists with developing a way to widen its effective range, possibly to strike as far as the US.
It was difficult because you had to get in a certain range. Even the V2s, which was really the first intercontinental ballistic missile, couldn't quite reach that far at that stage.
Once again, subs seemed to be the solution. But at 14 metres in length and weighing 12.5 tons, the V2s were too large to launch directly from a U-boat. But could they tow them instead? Engineers devised a plan where a single sub could pull 3 500-ton containers, each 45 metres long, with a V2 rocket housed inside. When they came close to the east coast of America, the platforms would be trimmed to a vertical position for launching. But once again, the Germans ran out of time. Only one submersible launching pad was ever completed before the war ended. As rudimentary as the design seems, it was an important step to how the submarine's battlefield role would evolve during the Cold War through to today. Two of their innovations had now failed to have the impact they hoped. But German engineers had another idea to help win the War of the Waterways. After almost 5 years of fighting, the Axis alliance controlled most of Western Europe. The Allies needed a major strategy to push the Nazis back and liberate occupied countries. And it would all start with the largest amphibious invasion in the history of warfare. D-Day was the beginning of a lengthy campaign that would ultimately lead to Hitler's downfall. But if one design had been completed in time, the outcome could have been very different. At the start of World War II, the might of the British Navy far exceeded Germany's small fleet of battleships, destroyers, and subs. But what the Nazis lacked in numbers, they made up for in speed. Schnellboots were the Messerschmitts of the sea, fast fighting craft, armed with torpedoes and machine guns. Half the length of a Type XXI U-boat and more than twice as fast, they were responsible for sinking over 100 merchant ships, 12 destroyers, 11 minesweepers, and numerous smaller vessels. They could outrun the enemy on the surface, which inspired the Germans to begin working on a new secret vessel that utilized hydrofoil technology.
A hydrofoil is a device similar to an aerofoil on an aircraft. It's on the hull of the boat and it lifts it out of the water and reduces the effect of drag, so it makes it faster.
Hydrofoils had been experimented with by many nations prior to and following the Second World War, with the first examples being built as early as the 1890s. By the early 1930s, multiple German engineers began producing military hydrofoil designs, one of which was Oskar Tietjens.
In 1937, Oskar Tietjens began working on this, and by 1941 he came up with the first test of it, which didn't work out very well. It took about 5 goes before eventually the Manta hydrofoil was come up with.
Operated by a 2-man crew, the Manta was constructed of 3 15-meter hulls that were connected to each other by a 6-meter wing. Extending from the outer hulls were 2 large keels. Connected to the keels were a fore and aft hydrofoil that would lift the Manta out of the water as it sped along. Tires, affixed to allow for access to and from the shore, assisted this process with their natural buoyancy. Propelled by 2 600-horsepower diesel-electric engines, the Manta could reach speeds of up to 50 knots and cover 200 nautical miles at that speed.
There was absolutely nothing as fast in any of the Allied navies. They couldn't have stopped it, they couldn't hardly detect it because it was so fast. Now, this was a really radical concept.
What was radical about the Manta was its combination of the speed of a hydrofoil with the stealth of a midget submarine. Midget submarines, submarines with a displacement of 150 tons or less, were crewed by 1 or 2 operators and armed with a similar amount of torpedoes. But midget subs were often poorly built, making many unreliable and somewhat of a death trap. To top it off, Their slow speed made making a clean getaway difficult, once an attack had been attempted and the alarm raised. The Manta would look to solve this problem by utilising its incredible speed to bring the craft to its target before submerging, where the banks of batteries stored in the keel would take over from the diesel fuel, propelling the Manta to speeds of up to 30 knots. The exceptional range of the Manta brought all of the channel ports within striking distance. Armed with sea mines or up to 8 torpedoes, the Manta had the firepower to make it count and the speed to make a clean getaway.
Of course, it had huge disadvantages. It was a massive gas guzzler. Hydrofoils and hovercrafts are all heavy on fuel and raw materials, which by the stage in the war that they'd reached, that was a premium. Everything had to be prioritised, and that was considered to be, well, yeah, it might be a good idea, but we've got more immediate things that we need to spend it on, like these tanks or these aircraft or these guns.
Unfortunately for Germany, in this case, practicality triumphed over vision. But if the Mantas had been let loose around the D-Day landing fleet, history could have been very different.
It was effectively a huge, massive weapon that would have made a difference if it had been available, and particularly would have been able to make D-Day virtually impossible. But not a single example was ever put into action. At the end of the war, they destroyed all the blueprints, and there's only one model of it that remained.
It was fortunate for the Allies the Manta never became a factor in the D-Day landings. As it was, they had enough obstacles to overcome to pull this mission off, as history had demonstrated all too clearly. On August the 19th, 1942, 6,000 Canadian, British, and American troops attempted a shore-based assault on the French port of Dieppe. Outgunned and outnumbered, they beat a hasty retreat just a few hours later. With less than half their men still standing, a radical rethink was required for any future attempts at beach-based landings.
In 1942, the coastal port of Dieppe had been raided, and it was realised then that the German defences were unduly strong, and that to attack a defended port would be tantamount to suicide, and that thousands of Allied personnel would be killed.
Over the next 2 years, the Nazis constructed a series of fortifications stretching more than 4,000 kilometres from France to Norway, a defensive system known as the Atlantic Wall. Faced with a virtually impenetrable shoreline, Allied command devised an ambitious plan to outsmart the Germans.
Allied planners realised that the success of the invasion of France in June 1944, Operation Overlord, or better known as D-Day, was dependent on successful resupply of the armies in France. They recognised that trying to pierce Hitler's Atlantic Wall and actually capture the strategic ports of Cherbourg, Calais and Le Havre was not going to be possible, and neither was it going to be possible to actually resupply the troops over open beaches. So the solution they arrived at was to construct 2 artificial harbours in Britain, which would then be towed across the English Channel to the French coast, where they would be anchored and then used as artificial ports.
An engineering feat of this scale had never been trialled before. To have any chance of success, the Allies had to catch the Germans off guard. The top-secret plan for these massive structures was codenamed Mulberry. To protect the invasion force from channel swells, a series of breakwaters would need to be constructed. Partially submerged steel barriers known as bombardons formed the first line of defence against waves. Their reach extended by the sinking of about 70 retired merchant and navy ships. Next came the caissons. Over 200 reinforced concrete blocks, measuring up to 60 metres long and 15 metres wide, and as high as a 5-storey building. Pierheads, codenamed spuds, would attach to a 1.6-kilometre pontoon bridge from the port to shore. Over 8 months, 45,000 people worked to construct the components in factories and dry docks around the country to meet the deadline for D-Day.
The contractors were only given enough information to build the particular structure that they were commissioned to build. So none of them had the entire set of plans, and none of them knew exactly what the final shape of the Mulberry Harbours was going to be, or indeed what the end use was going to be and where.
As D-Day dawned, 7,000 ships and landing craft descended on the Normandy coast, carrying more than 130,000 Allied troops. Now it was time for the 1.5 million tons of harbour hardware to make the more than 150-kilometre journey across the sea to France.
So while the landing forces were hitting the beaches on the 6th of June, the sections of Mulberry Harbour were being towed across the channel, and the first section arrived off Arromanches on the morning of the 7th of June, so less than 24 hours after the landings. From that point, sort of the block ships were dropped in both the British sector and the American sector, and within days the ports were up and running.
Each of the hollow concrete caissons weighed up to 6,000 tons on the surface. They were towed to predetermined positions on floating platforms. Then, sea valves were opened to flood their internal chambers, allowing a carefully controlled descent onto the seabed 10 metres below. Once the caissons were in place, construction went into overdrive. With millions of tons of supplies needing to be brought ashore over the next few months, the harbours had to be operational around the clock. Electric winches raised and lowered platforms on the pierheads to allow for the 6-metre tidal range off the Normandy coast. 9 days after the D-Day landing, Mulberry A was up and running in the American sector off Omaha Beach. Mulberry B followed a few days later in the British sector off Arromanches, 20 kilometres away. In the first week alone, the Allies were able to offload 200 ships and 180,000 men. The vital supply chain was now secure to support the Allied troops' advance across France. The Mulberries were only ever intended as a temporary measure until the German-held ports could be liberated. But one of these harbours' design and longevity was about to be put to the test.
Shortly after D-Day, one of the biggest storms in 2 generations blew up over the Normandy coast, causing massive damage to the 2 Mulberry harbours. The American harbour at Omaha was severely damaged and put out of action. Mulberry B in the British sector was damaged but still operational. It was decided not to fully repair Mulberry A at Omaha, and most of the restructuring of Mulberry B at Arromanches was successful and enabled it to continue in use until October 1944. Mulberry B was critical to the successful campaign in Normandy. It enabled 40,000 vehicles, 220,000 troops, and over 500,000 tons of supplies to be landed through the Mulberry B harbour between June and October 1944.
Such was the success of this engineering feat. Albert Speer, the Reich's Minister for Armament and War Production, conceded post-war that the idea was simple genius. The Mulberry harbours had demonstrated the benefit of thinking outside the box, but the British had another left-of-field idea that could potentially regain them dominance of the Atlantic. Britain was in a desperate position midway through the war. The German naval campaign had been so effective in sinking Allied supply ships, the island nation was at risk of running out of vital military materials. The biggest danger zone was mid-ocean, where shore-based air cover couldn't protect the convoys from submarine attack. Churchill needed a radical idea, too big to fail, but one that wouldn't put any undue pressure on his dwindling stock of steel.
At the time, the Battle of the Atlantic was raging. Air power formed a crucial part of fighting the battle because anti-submarine patrols were used to detect German U-boats, and because of the range of aircraft, there was a gap in the mid-Atlantic.
The solution: build the world's biggest aircraft carrier. The HMS Habakkuk would be dominated by a runway over 600 metres long, 91 metres across, and displace approximately 2 million tons. Dwarfing the largest US aircraft carrier in World War II, the Lexington-class USS Saratoga. It would triple the aircraft capacity of the Saratoga too, carrying 200 Spitfires and 100 Mosquitoes.
So with Habakkuk, it was thought that the ship could be constructed, it could be based in the northern areas, around sort of Greenland, Iceland, and sail around sort of the general Arctic area, where it is relatively cold, fly off her aircraft and close the mid-Atlantic gap.
But conventional materials like steel and aluminium were in short supply, so the designers came up with a novel solution: construct it out of ice. Ice could be manufactured using 1% of the energy required to make steel. But there were major concerns about its durability. Would this floating carrier melt away when things heated up? The plan was altered from building Habakkuk out of pure ice to creating a composite material using wood pulp called picrete. It would liquefy slower and be comparable in strength to concrete. Admiral of the Fleet, Lord Louis Mountbatten, just needed to convince Prime Minister Churchill this was now a viable option, which involved an urgent visit to his country house.
The story goes that Churchill at the time was in Chequers, and that when Mountbatten arrived, he was in the bath. So undeterred, Mountbatten strode into the bathroom and told Churchill about picrete and dropped the block into the bath. And Churchill realised that the block wasn't melting and became on board with the project.
Despite its heavyweight backing, the project was plagued with problems. To achieve the specifications demanded by the Navy, it would take an estimated 300,000 tons of wood pulp, 35,000 tons of timber, and 10,000 tons of steel. The original production budget of 700,000 British pounds would be closer to 10 million pounds. In today's value, that's over 716 million pounds.
it was realised that a vast amount of pipecrete would need to be constructed, and that the steel required to construct the refrigerators and the freezers to produce such a vast amount of pipecrete would outweigh a full fleet of conventional aircraft carriers.
Project Habakkuk was scrapped, but it wasn't a total loss. The composite material invented for its design would have other uses down the track.
Pipecrete in the Second World War after Habakkuk was sort of left on its own, but in more recent years there have been buildings that have been constructed out of pipecrete in, say, Arctic Norway or the very cold regions, where you can construct buildings relatively easily and cheaply. It's low cost, it's hard wearing, and to a degree it's fairly environmentally friendly because ultimately it is just water and wood.
Some of the war's boldest ideas did make it beyond the planning stage, even if they were never used to their full potential. In 1933, Japan walked away from the League of Nations after being reprimanded for invading the Chinese province of Manchuria.
Japan, however, finds it impossible to accept the report adopted by the Assembly.
The island nation was now on a collision course with its two regional rivals, America and Britain. If a war was declared, Japan had no hope of producing the volume of warships needed to win such a battle. The only option was to build bigger and better. So work began on the Yamato-class battleships.
Yamato was constructed at Kura in Japan amidst great secrecy. She was constructed during the late 1930s and through 1940. There was no limitations placed on the design of the ship. It was designed to be as big and as powerful as the designers wanted. So with that, a number of challenges had to be overcome. One of the principal ones was how to create a ship of such a size.
To be able to take hits from the most powerful naval guns and keep fighting, the Yamato's design called for truly staggering amounts of steel. At 41 centimeters thick, her hull armor was far stronger than any battleship designed before. This deep steel casing accounted for a third of Yamato's more than 70,000-ton displacement. By comparison, the largest battleships the US Navy would field during the war were 52,000 tons.
During the early 1930s, the Japanese were getting to grips with welding. A lot of ships at the time were still riveted. Welding saved a lot of time and effort and money, and also created more of a flat surface, which was more conducive to gaining speed.
The sleek lines afforded by the welded steel was complemented by a bulbous bow design, which further reduced drag, allowing her 150,000 horsepower steam engine to achieve speeds of 27.5 knots. On her deck, she carried 3 triple gun turrets, each weighing as much as a typical American destroyer.
So the Yamato was armed with the largest guns ever fitted to a warship. They were 18.1 inches in diameter. In comparison, the largest guns mounted on an Allied warship was 16 inches.
The main guns were able to hurl 1,500 kilogram high explosive or armor-piercing shells, more than 40 kilometers. Yamato's capabilities and construction were kept under an effective veil of secrecy. The US had no clue of her existence until midway through the war.
She began her sea trials in 1941. Ironically, she was conducting her final sea trials for commissioning as the Japanese were launching their attack on Pearl Harbor on the 7th of December 1941.
As the war went on, the vulnerability of battleships to sustained aerial attacks and the effectiveness of aircraft carriers relegated many to largely support roles. The Yamato was no different. Too valuable to risk and too vulnerable to be effective, it operated as a glorified troop transport for much of the war. That was until the final desperate battle of the Pacific campaign.
First of April 1945, American forces landed on Okinawa, which was to be the final stepping stone before the invasion of the Japanese home islands. So the idea was that the Yamato, along with a cruiser and a number of destroyers, would sail to Okinawa from Japan, and the plan was they would conduct a fast run at the beachhead and in a single pass would try and cause as much damage amongst the transport and landing ships as possible, whereupon Yamato would be beached on the island and her guns would then be used as a gun battery, and the crew would be disembarked and would join the troops fighting on the island as infantry.
But it wasn't to be.
During the early hours of the 7th of April, the American aircraft began to take off from the aircraft carriers and around noon located the Yamato and her accompanying ships. So 3 waves of aircraft attacked over a period of approximately 2 hours, during which the Yamato sustained approximately 11 torpedo hits. The Yamato began to take on so much water that she capsized. As she capsized and sank, the ammunition in her magazines exploded and it created a mushroom cloud which reached a height of 3.5 miles and was seen approximately 100 miles away on Kyushu.
It seemed a fitting finale to Japan's naval campaign. Its figurehead lost beneath the waves after a final desperate attempt to save the country.
There's a number of films which have been produced glorifying the final operation of the Yamato and her sinking. So she's very much a part of Japanese culture. At the same time, though, she is the battleship which could have accomplished so much more had sort of naval doctrine not switched towards the aircraft carrier. Had she been involved in a battleship engagement as seen in the Mediterranean, or indeed fought by the British against Bismarck, then it would have been interesting to see what the results would have been.
With naval campaigns playing such a big role in the outcome of World War II, both the Allies and the Axis alliance understood the importance of continually developing weapons that could help dominate this challenging environment. So many innovative ideas had the seeds of success, but neither the time nor the resources to grow them into fully functioning options. For those that did work, it wasn't all about firepower. Sometimes the simplest solutions helped pave the path to victory. And for the thousands of concepts designed in secret but never adopted, who knows how different our world would be if these weapons had ever got beyond the drawing board.